Imagine standing on the surface of Mars right now, where your blood would boil in seconds and the cold would freeze you solid before you hit the ground. And then imagine fast forwarding to a day when you could walk outside in a t shirt and take a deep breath of fresh air. We actually have two completely different blueprints to make that happen, and they are about to go to war with each other. We are looking at the ultimate engineering challenge in the universe. On one side, we have the mechanical approach, which we call terraforming. This is the heavy lifting strategy. It involves brute force, massive machines, and raw energy to beat the planet into submission until it looks like Earth. On the other side, we have seeding. This is the biological approach. It is much quieter. It is about using tiny living things to slowly eat the planet and change it from the inside out. The title slide here sets the stage for a scientific and economic fight between these two distinct philosophies for planetary transformation. This isn't just about science fiction anymore. We are analyzing the actual costs, the time it takes, and the tools we need to physically change a dead rock into a living world. We have to decide if we want to build a planet like we build a skyscraper, or if we want to grow a planet like we grow a forest. Let us start with where we are right now. Mars today is a frozen desert. The air is so thin it is barely there. Cosmic rays slap into the surface constantly because there is no magnetic shield. If you stood there, you wouldn't just suffocate, the radiation would tear your cells apart. The goal for everyone is the same, a future Mars where you can walk around in a shirt sleeve environment. We want breathable air and liquid water. On the left, we have terraforming path. This path creates a global change. It tries to fix the whole planet at once. It is incredibly cost and time intensive because you are fighting physics directly. You are trying to heat up an entire world using machines. On the right, we have the seeding path. This is a slow motion garden approach. It relies on self-repairing biology. It uses targeted growth where we only fix small patches at a time. Think of terraforming as installing a massive HVAC system in a broken house, while seeding is planting ivy that slowly covers the cracks and seals the leaks over thousands of years. The seeding method is marked as targeted and efficient because biology does the work for you for free. Let us meet the fighters in this cosmic ring. In the red corner, representing massive engineering and rapid climate change, we have terraforming. The goal here is specific, getting the temperature to 21 degrees Celsius and the air pressure to 1 bar, which is exactly what we have on Earth in just 300 years. That is lightning fast in geological time. The weapons of choice here are orbital mirrors to focus sunlight, greenhouse gas factories to pump out heat trapping air, and nuclear engines to melt the ice. The budget trillions of dollars upfront. It is like buying the planet a new atmosphere with a credit card. In the green corner, representing biological engineering and long term adaptation, we have seeding. The method here is totally different. We use algae, moss, and microbes. These tiny creatures exhale oxygen, glue toxic dust together to make soil, and invite plants to grow. The budget is much smaller, billions instead of trillions, but the catch is the wait time. This means waits millennia. It is resilient. We are talking about sun tough algae and engineered microbes that can survive on a dead world. Now we get into the heavy machinery of terraforming. This is the space mirror method, basically a cosmic magnifying glass. Imagine a mirror that is 200 kilometers wide floating in space. It isn't glass, it is a shiny foil, almost like a giant pizza made of aluminum wrapper. The plan is to park this giant reflector in orbit and angle it so it catches sunlight that would normally miss Mars and bounces it directly onto the Martian South Pole. It focuses heat like a laser. We are talking about 1000 megawatts of focused energy. This heat hits the dry ice frozen carbon dioxide at the pole. The ice doesn't melt into water, it sublimates, turning instantly into gas. This thickens the atmosphere. A thicker atmosphere traps more heat, which releases more gas, creating a runaway greenhouse chain reaction. But looking at the logistics, this is a nightmare. Each mirror requires 100 launches of a massive rocket like the SpaceX Starship. The cost per mirror is around $100 billion. We would need 50 of them working for 50 years just to raise the temperature by 5 degrees Celsius. It works, but it is a brute force engineering at its most extreme. If mirrors aren't enough, we build factories, but not factories for cars or phones. These are robotic gas factories, and the best way to think of them as a is a nuclear powered waffle irons. We send 5,000 of these robotic units to the surface. They crawl around, scoop up the Martian red dirt, and bake it into a chamber at 600 degrees Celsius. They are powered by compact nuclear reactors because there are no power outlets on Mars. When you bake the dirt, it releases fluorine gases. We want to release fluorine based super greenhouse gases because they are 17,000 times stronger at trapping heat than regular carbon dioxide. It is like putting a super thick wool blanket on the planet instead of a thin sheet. The goal is to get the temperature to zero point 0.3 bar in 100 years. That is enough pressure that your blood won't boil and you could walk outside with just an oxygen mask instead of a full spacesuit. The price tag for this layer of the project is $2 trillion, which is roughly the cost of building 2,000 skyscrapers on Earth. Method number 3 is the most violent. We call it asteroid redirection. This is essentially throwing mountain-sized snowballs at the planet to create steam. We find icy asteroids about 10 kilometers wide floating in outer solar system. We attach massive engines to them. We could use solar sails that ride on light pressure or ion thrusters that gently push the rock for decades. We guide them onto a collision course with Mars. When they hit, the impact releases energy equivalent to 10,000 hydrogen bombs. This violence serves a purpose. It instantly vaporizes the ice in the asteroid and the ice underground on Mars, filling the air with water vapor and dust. This acts as a blanket, trapping heat and thickening the atmosphere. But the risks are obvious. If you miss your target, you could destroy the infrastructure you already built. It is uninsurable damage. Plus, you are nuking the planet you want to live on. The propulsion cost alone is estimated at $500 billion. One big problem Mars has is that it lost its magnetic field billions of years ago. That means the sun strips away its atmosphere constantly. To fix this, we need an artificial magnetosphere. Think of this as a giant invisible umbrella made of lightning. We can't restart the planet's core, so we build a fake one in space. We launch 50 superconducting satellites and arrange them in a ring. They generate a 1 gigawatt plasma shield. This magnetic force field deflects the solar wind around the planet, allowing the atmosphere to heal and thicken naturally over time. This project takes 20 years to build and costs $300 billion. But here is the catch. It requires constant fuel and maintenance forever. It is an electric bill that future Martians will have to pay every single month. If the system fails, the atmosphere starts leaking away into space again within mere centuries. It is a permanent life support machine for the entire world. Now let us switch to the biological approach. Instead of nuclear explosions, we use the algae pioneers. We aren't just sending pond scum, we are sending genetically edited survival experts. In the lab, we edit the DNA of microscopic algae cells to withstand the hellish conditions of Mars. We give them purple pigments to act as sunscreen against UV radiation. We tweak them to resist cold down to minus 60 degrees Celsius. We adapt them to survive in low pressure, as low as 0.006 bar. We drop these cells into salty meltwater ponds on the surface. They soak up the radiation and eat the salts. In return, they do something magical. They exhale oxygen bubbles. Imagine millions of tiny biological balloons floating up from the dirt. The launch cost is incredibly cheap compared to mirrors. We can send 100 capsules for just $5 billion. Over 20 years, these algae form mats on the ground. By year 20, we could have 1 centimeter thick algae mats covering 5% of Mars. It is slow, but it is happening automatically. The seeding process isn't just about air, it is about turning dead rock into living soil. This is a 3-step relay race. Step 1 is algae and crust formation. The algae secrete sticky sugars that glue the toxic dust together into a stable crust. This stops the dust storms from blocking the sun. Step 2 brings in the lichen. Lichen is a tough organism that eats rocks. It secretes acids that chemically crack the rock stones, turning them into sand. It builds about 1 millimeter of new soil every decade. Step 3 is moss. Moss holds 10 times its own weight in water. It acts as a sponge. It also insulates the microbes living underneath it and darkens the surface color. Darker colors absorb more heat from the sun. So the moss actually warms the ground by about 0.2 degrees per century just by being there. The economics here are wild. While terraforming costs trillions, seeding stays under $20 billion because life multiplies for free. You send one packet of seeds and a million years later you have a forest. We need to talk about what is happening inside that moss. This is the microbial chef approach. The Martian atmosphere has nitrogen, but plants can't eat gas. They need it cooked into a solid form like ammonia. That is where our microscopic chefs come in. We engineer bacteria to live inside the stems of the moss. These bacteria pull nitrogen gas from the air and cook it into biofertilizer that the plants can use. It is a symbiotic kitchen. In the lab, we see exponential growth. On day 0, we release them. By day 30, the population has multiplied 1000 times. By day 200, you could have more bacteria than there are stars in the observable universe if they had enough food. The total startup cost for this gene editing and the rover spreaders to distribute the bacteria is only $1 billion. It creates a fertile soil timeline where you could have dandelions and wheat growing in open soil in 200 years. Biology is usually slow, but we have a way to hit the fast forward button. It is called CRISPR-Cas9. This is a gene editing tool that acts like molecular scissors. In an Earth lab, we can take a regular tomato seed and turn it into a Martian superhero seed in a single afternoon. We don't have to wait for evolution to get lucky. We cut the DNA and paste in the traits we need, like cold resistance or drought tolerance. We test these new varieties in Mars simulation chambers on Earth, freezers set to vacuum pressures. This gives us a massive speed up. Traditional seeding might take 30,000 years to make crops ready for Mars. With CRISPR, we shave millennia off the calendar, achieving the same result in just 300 years. That is a 1000-fold speed up. For a development cost of $10 billion, we get crops ready for outdoor planting centuries ahead of schedule. Let us look at the bill for the mechanical terraforming method. The total estimated cost is $8.5 trillion. To break that down, the space mirrors cost $5 trillion because of the launch costs. The greenhouse gas factories cost $2 trillion. The asteroid missions cost $500 billion. The magnetic shield is $300 billion. And you need $700 billion for rockets, labor, and inevitable mistakes. To put $8.5 trillion in perspective, that is about 8% of entire global GDP for a year. It is the same price as building 850 new aircraft carriers. If you spread this over a 50-year deployment scenario, the yearly spending is about half of US military budget. A relatable analogy for how much money that this is, it is equivalent to buying every single person on earth, all 8 billion of us, a $1,000 tablet computer, and you would still have change left over. It is an astronomical amount of money. Now we compare the two checkbooks. Seeding is the smart biology approach. The algae starter cultures cost $5 billion. The CRISPR labs cost $10 billion. The lichen and moss packets cost $15 billion, and the bacteria brew are $1 billion. You add in $20 billion for small rockets and rover gardeners to spread the seeds, and the grand total is $51 billion. That is less than the cost of building one district in Dubai. The reason seeding wins on price is biological reproduction. Nature does the heavy lifting. Once you plant the life, it copies itself for free. The long term costs drop toward zero because the ecosystem runs itself. With terraforming, the costs stay high forever because machines don't have babies. You have to keep repairing the mirrors and fueling the factories. The graph shows a stark difference. Terraforming is a flat line of high expenditure, while seeding curves down to almost nothing. When we stack the resources side by side, the difference is staggering. We have $8.5 trillion for terraforming against $51 billion for seeding. That creates a ratio of 167. It is 167 times cheaper to seed the planet than to terraform it. Look at the physical material needed. Terraforming requires 100,000 rocket launches to get all that steel and fuel to Mars. It requires millions of engineers working with steel, uranium, and rocket fuel. Seeding requires only 200 launches. We only need thousands of biologists working with DNA, petri dishes, and greenhouses. The analogy here is perfect. Seeding wins the cost contest for a kid's saving allowance, even if it takes 10 times longer to finish the job. It is the difference between buying a pre made mansion or buying a bag of acorns to grow a forest. If we choose the expensive terraforming route, here is the schedule. It is a multi generational project but fast by cosmic standards. Year 0 is launch and infrastructure. By the year 10, the first mirror is hitting the pole and the temperature rises by 1 degree. By year 30, the carbon dioxide atmosphere thickens and we might see the first liquid water streaks. By year 70, we hit a big milestone, 0.3 bar of pressure. The noon temperature at the equator hits 20 degrees Celsius, shirt weather, but you still need an oxygen mask because the air is poison. By year 200, the pressure is higher, but oxygen is still at 0%. It isn't until year 300 that we import enough plants to get oxygen to 21%. That is the finish line. Kids born today would see their great grandkids having a picnic on Martian grass. It takes about 10 generations of humans to complete. Now look at the seeding timeline. This requires patience on a geologic scale. Year 0, we sprinkle the algae spores. By year 20, green ponds are visible from orbit. But things move slowly. It takes until year 100 just to get lichen carpets covering 10% of surface. By year 500, we have moss forests darkening the soil. The atmosphere doesn't become breathable for a long time. By year 2000, we might see grass like plants. By year 10,000, insects could survive. But to get full earth like air with 21% oxygen and towering trees, we are waiting until year 50,000. The oxygen levels climb painfully slowly, 0.1% to 1% to 5% over millennia. The total wait is 2000 generations. Kids today would need 1600 more family trees to breathe free on Mars. That is longer than the entire history of human civilization on Earth. So, how do we choose? It depends on the goal. If the goal is speed, terraforming is the clear winner. It gets us liquid water in 30 years. That is 170 times faster than seeding for creating a wet planet. It gets us breathable air in 300 years. But if the goal is sustainability, seeding wins. Seeding creates a self-sustaining biosphere that doesn't need constant repairs. It gets us green patches in just 20 years, which is 3 times sooner than terraforming. Terraforming is for impatient explorers who want results now and have the money to burn. Seeding is for long-term gardeners who want to set it and forget it. If the goal is liquid water alone, terraforming wins at 30 years. But if the goal is a biosphere that runs itself, seeding eventually catches up and keeps growing without extra bills. The terraforming path is fraught with danger. We are talking about planetary perils. The first risk is a misaimed asteroid impact. One calculation error in the trajectory could obliterate half the planet. The impact energy is huge and a mistake is catastrophic. Second, the orbital mirrors can malfunction if one gets stuck focusing on the wrong spot or they don't move together. You create uneven heating that drives 300 km per hour superstorms. You could accidentally freeze one side of the planet while roasting the other. Third, the greenhouse gas factories are basically pumping out super poisons. If there is a containment breach or they explode, we release toxins that could kill any life we are trying to save. Fourth, overwarming is a real threat. We might melt permafrost that releases ancient, dormant microbes that are deadly to Earth's life. And finally, economic collapse. If the funding stops halfway through, the planet cools down, the atmosphere fizzes out, and the whole project is lost. Models suggest a 30% probability of at least one major disaster. Seeding seems safer, but it has its own horror stories. The seeding dilemma involves creating life that we can't control. First, there is the mutation risk. We release engineered green algae, but cosmic radiation mutates it into a black sludge. This slime could be resistant to everything, smothering the ecosystem and turning the oceans into black goo. Once it's out there, you can't recall it. Second, there is a geochemical hazard. The lichen produces acid to eat rocks. If that acid leaches into the groundwater, it could poison the future water supply for colonists. Third is the fear of bacterial evolution, the Mars flu. The bacteria we send to help plants could evolve to attack human lungs instead, creating respiratory illnesses we have no cure for. While terraforming risks are explosive, seeding risks are like a slow cancer. The damage is ecological and might not be detected for centuries until it is irreversible. There is also a philosophical battle here, preservation versus transformation. Terraforming is aggressive, it erases the original state of Mars. We are painting over a rare fossil. By melting the surface and flooding it, we destroy 4 billion years of geological history. If there are native microbes sleeping in the dirt, terraforming wipes them out before we even find them. It is like ripping out an old library to build an amusement park. Seeding is gentler. It adds to the existing world like adding a new book to the library one at a time. We assume the surface is lifeless, so we just add a thin layer of life on top. It preserves the alien deserts for study. If we make a mistake, seeding is easier to halt or adjust because it moves so slowly. Terraforming is hard to stop once the chain reaction begins. The energy required to terraform Mars is almost impossible to comprehend. We need to move 50 asteroids and build thousands of factories. The total energy budget is estimated at 1.5 times 10 to the power of 20 joules. To break that down, the asteroid impacts alone release 1 times 10 to the power of 20 joules, which is equal to about 2 years of entire human race's total energy consumption. Then, to keep the planet warm, we need another massive chunk of energy constantly. It is analogous to running 30,000 Hiroshima bombs worth of energy just for the impacts. For the maintenance, think of it like running 500 giant toasters forever. We are talking about 500 nuclear reactors years of energy output. It is a project that demands we harness the power of a star and focus it on a single rock. This slide shows only this slide shows why seeding is so efficient. It leverages the cosmic energy equation. In seeding, we capture free star power. The algae perform photosynthesis, which is about 3% efficient, but they do it over millions of square kilometers for free. The sunlight hits the algae and they grow. Over a lifetime, the net energy captured is massive. We put in a tiny amount of energy to launch the robots, 1 times 10 to the power of 70 joules, and the biological system captures 3 times 10 to the power of 20 joules from the sun. That is a huge profit. It's like planting a seed that grows into a solar panel tree powered by the sun forever. Terraforming is the opposite. It requires artificial energy injection. We have to pump energy in constantly, 3 times 10 to the power of 16 joules every year just to keep the lights on and the heat up. The net energy profit is negative. because we are always paying the bill. It is like trying to find trying to fill a leaky bucket with water forever. It needs constant effort. Seeding gives us an energy return on investment of 30,000 times because nature does the work. We aren't just guessing that this will work, we are rehearsing on Earth. We use analog environments in Antarctica and Siberia as cosmic rehearsal theaters. In Antarctica, we have tested the mirror concept by using reflective arrays to bounce sunlight into a frozen valley. Researchers achieved a localized heating of 2 degrees Celsius. It proves the physics of the mirror method works in a frozen desert. In Siberia, scientists have tested greenhouse gas generators. They set up an array of factories to thicken the winter air with heavier gases, achieving a 0.1% concentration increase, which helped trap heat. These sites feed data into computer models that give us 80% confidence in our Martian predictions. If our machines can survive minus 50 degrees and hurricanes winds on Earth, they have a fighting chance on Mars. We also look back at historical experiments where we tried to build mini worlds. In the 1970s, the Soviets built BIOS 3 in Siberia. It was a closed steel tube where algae cultivators recycled the air for a crew of 2 to 3 people. The result was a success. Algae alone maintained oxygen levels for 6 months. But then there was Biosphere 2 in Arizona in the 1990s. This was a massive glass greenhouse with a rainforest, ocean, and savanna inside. It failed. Oxygen levels dropped mysteriously. It turned out that the overlooked microbes in the soil were eating the oxygen faster than the plants could make it. They had to pump in air to save the crew. The lesson was critical. Tiny microbes control big atmospheres. If you miss one species in your list, the whole system crashes. This taught us that for Mars, our species list must be exhaustive and perfectly balanced. Right now, astronauts on the International Space Station ISS are running the Algae Pioneers pilot episodes. They are testing how algae handle microgravity and radiation. They found that green algae can recycle 20% of an astronaut's carbon dioxide breath into oxygen within 24 hours. They also optimized the lighting. By using flashing blue and red LED lights, they doubled the growth speed of the algae. One big challenge was strange clumping. In zero gravity, the algae don't float evenly. They clump together and suffocate. The fix was a motorized steering solution to keep them moving. Crucially, the algae survived radiation doses 100 times higher than normal Earth's. This boosts our confidence that they can survive the trip to Mars and harsh surface conditions. Here is the hard reality of math. The atmospheric scale is massive. To get Mars to Earth pressure of 1 bar, we need 2.5 times 10 to the power of 18 kilograms of gas. That volume is equal to 500,000 Empire State Buildings made of solid air. Terraforming plans to get 90% of this from vaporizing the poles and asteroids. Biology, however, is too slow. Even after 50,000 years of seeding, the plants will have only produced 1 times 10 to the power of 16 kilograms of gas. That leaves 99% of atmosphere missing. The biology can make oxygen, but it can't make enough pressure to hold it down. This leads to a critical conclusion. Seeding must partner with geology. We can't just plant trees, we have to melt the ice too, or we will have to accept a thinner air forever, where we always need pressure suits. The deployment strategy differs too. Terraforming is a planet-wide, all-or-nothing game. It is like building a giant swimming pool and waiting 100 years to fill it before anyone can jump in. We have to create the entire atmosphere first before you can establish cities or ecosystems. Seeding is incremental. It offers early access. We can build small algae bioreactors that capture oxygen immediately for a small base. We can harvest oxygen from a 10,000 square kilometer patch to support a settlement of 1 million people. It scales to settlements. We don't need to change the whole world to start living there. We can have little green oases. It supports immediate needs while the global biosphere slowly wakes up. It's like building a small kiddie pool first and letting the kids play while you dig the big pool in the background. Heat is the master variable. Mars is freezing. We need to raise the temperature by 5 degrees Celsius just to start the chain reaction. This requires 1 times 10 to the power of 23 joules, which is equal to 3 minutes of all the sunlight that hits Earth. Terraforming uses active heating. The orbital mirrors act like a giant hair dryer on a low setting, constantly pumping in heat. Seeding uses passive absorption, darkening soil by covering the light red dust with dark green moss and algae. The ground absorbs more sunlight. It is like dark t-shirt analogy. You get hotter in a black shirt on a sunny day than a white one. But biology is slow. While mirrors can do the job in 30 years, the moss method takes 3000 years to absorb that much heat. If we plot this on a graph, the difference is visual. The y-axis is cost in billions and the x-axis is time in years. Terraforming is a steep, vertical climb. It spikes immediately to $8.5 trillion in the first 300 years. It is the steep, expansive hill. Seeding is a long, flat line at the bottom. It hugs the x-axis, never rising above $51 billion, but it stretches out to year 50,000. It is a long, cheap road. There is a value for money intersection around year 1000, where the patience pays off. The graph has colored zones. The green zone is within a human lifetime. Terraforming wins here for water. The yellow zone is multiple generations. The red zone is deep time, where seeding eventually finishes the job for pennies on the dollar. So, how do we decide the winner? It is a balance of risk and reward. Terraforming offers a giant reward of high habitability and a full biosphere, but it carries a giant risk of bankruptcy and planetary catastrophe. Seeding offers a modest reward of localized sustainability and an initial presence with a gentle risk profile. The smartest path might be a hybrid. We call it seed first, terraform later. Stage 1 is seeding for the first 200 years. We use biology to anchor the soil and create a base layer of life. This anchors the dust and proves the budget is reliable. Then in stage 2, we add the mirrors and accelerate the warming. Finally, in stage 3, we go for full terraforming. This way, if the money runs out, we still have a living world, even if it is a quiet one. It is the safest bet for our cosmic future. In the end, the choice between building a world and growing one might not be a choice at all, but a sequence. We might start as gardeners, planting the first seeds in the red dust, and graduate to become planetary architects, constructing a new earth in the sky. Either way, the red planet is destined to turn green. So, we just looked at the receipt for building a second home, and the numbers are terrifying. We are talking about burning the combined energy of a star and the wealth of 10 generations just to turn a frozen rock into a place where we might survive if we wear a mask. It makes you wonder if we are solving the wrong problem. We are sitting on the only known paradise in the universe, a world with perfect gravity, a free magnetic shield, and the air that fills our lungs for free. Instead of spending trillions to drag buckets of water to a dead desert, the smarter engineering challenge might be fixing the leaks on the ship we are already flying. We have limited resources in the physical world and atoms are expensive to move, but bits are cheap. If we want infinite frontiers, we don't need rockets. We can build a billion perfect worlds inside a server for the cost of one rocket launch. We can explore every possibility in a virtual utopia without scratching a single real mountain or polluting a single real river. Maybe the ultimate sign of an advanced civilization isn't that they spread out to consume the galaxy, but that they grew smart enough to stop consuming, turned inward, and realized that the best planet in the universe is the one they were born on.